So discuss about the distribution system classification, normal classification of distribution system, that is primary and secondary. After then we have to discuss the load modeling and its characteristics. Then some factors utilized for calculate the load on distribution system, that is demand factor, load factor, plant capacity factor, utilization factor, loss factor, contribution factor, coincident factor. After then relation between the load and loss factor. Then last one, different types of loads. Only 3 questions. So load modeling and its characteristics, relation between load factor, loss factor, different types of loads and its characteristics. Among these 3, last 2, that is relation between load and loss factor, different types of loads are very, very important. Every paper, these 2 will be incorporated first in it, and some problems, right? Now go to the problem. The first problem is the annual peak load of primary feeder is 2000 kilowatt, at which the power loss or copper loss is 80 kilowatt per 3 phase. Assuming an annual loss factor of 0.15, now determine first one, average annual power loss. Second one, the total annual energy loss due to the copper loss of the feeder circuit. So to find out the annual power loss and also annual energy loss also we have to determine. First one, average power loss. Average power loss. Second one, annual power loss or annual energy loss. So to find out the average power loss is nothing but we know the loss factor formula or definition of from the loss factor. So loss factor is the ratio of average power loss to the power loss at peak load. We know the loss factor and we know the power loss at peak load. From the given problem, loss factor is 0.15, power loss is 80 kilowatts. Therefore, average power loss is equal to multiplication of or product of loss factor multiplied with power loss at peak load. That is 0.15 into 80, that is 12 kilowatt for 3 phase. From that, to find out the annual in the sense, so for a year 8760 hours is there. So now the annual energy loss or annual copper loss equal to average power loss multiplied by 8760 per year. So that is 12 multiplied by 8760. So that is 163128 kilowatt hour. This is a simple problem, right? All of you note down. Next, second problem. The annual average load is 1234 kilowatts and monthly peak load is 3600 kilowatt, monthly or yearly, no problem. Both are same. Find the load factor and loss factor using approximate formulas. So to find out the load factor is the ratio of average load by maximum demand. The given average load, the given peak load, that is nothing but maximum load. So both are same, both are given. Directly find out the load factor, FLD equal to average load by peak load, and then find out the loss factor by using approximate formula. Approximate formula is nothing but the relation between load and loss factor. FLS is equal to 0.3 FLD plus 0.7 FLD square. From that formula, we have to determine the loss factor. They don't ask like this using approximate formula. You can utilize average power loss by power loss at peak load. Otherwise, just we have to the given directly approximate formula. That's why. So we have to utilize the relation between load and loss factor. FLS is equal to 0.3 FLD plus 0.7 FLD square. So first of all, the given. So average load and peak load. Therefore, load factor is equal to average load by peak load 1234 by 3600. Don't confuse, this is a monthly. So here in distribution, maximum monthly or yearly, peak load is same. So that's why I'm taking peak load of, that is 1, 2, 3, 4. So peak load is 3600. The value load factor is 0.3428. Now approximate formula derived by the Woodruff. Loss factor is 0.3 FLD plus zero point 0.7 FLD square. So 0.3 into 0.3428 plus zero point 0.7 into 0.3428 square. So value is 0.185. Sometimes asking this type of simple problems also. Suppose they are asking for A bit, derive the relation between load and loss factor. And they are asking B bit like this for problem 1 or problem 2. So for at that time, so derivation is taken for 7 marks or 8 marks. So problem is 2 marks. Next problem 3. Find the annual load factor and average demand given that peak load is 3.5 megawatt. Unit supplied is 10 million. Unit supplied is 10 million. Find the annual load factor and average demand given that peak load is 3.5 megawatt and unit supplied is 10 million. They don't given in bracket 10 power 7 kilowatt hour. In general examination, they don't given 10 power 7 kilowatt hour. They given just 10 millions. We know that 1 million is equal to 10 power 6, right? 10 million is nothing but 10 power 7. Unit supplied is nothing but kilowatt hour, right? So unit supplied equal to number of unit generated equal to 10 millions, that is equal to 10 into 10 power 6, that is equal to 10 power 7 kilowatt hour. So you can write 1 million is equal to 10 power 6 in bracket. So the given peak load 3.5 megawatt, right? And the number of units generated or number of units supplied is 10 power 7 kilowatt hour. Now first we have to find out average demand or average load. Average load is nothing but number of units generated or number of units supplied divided by, so time taken by the year, a month, year or day, whatever it may be. Here they taken annual, that's why year. Annual average load equal to number of units supplied divided by hours in a year. Therefore, number of units supplied equal to 10 power 7. So 10 power 7 by 8760. The value is 1141 kilowatt. As we know, the average load is nothing but you can find out easily load factor. Why? Because load factor equal to average load by maximum demand. So annual load factor equal to average demand divided by peak load. So here already the average demand is nothing but annual. That's why we cannot put 8760 here. So 1141 kilowatt divided by 3.5 megawatt. So 0.325. Load factor is 0.325. All of you writing so don't write problem number 4. Just wait 1 minute. Why? Because so I am telling one problem. That problem is coming December 2017. Similar to that 3 problems. Similar to the third problem or first problem. So please note down the December 2017 problem. Not in problem 4. So please write down. A feeder supplies 2 megawatt to an area. A feeder supplies 2 megawatt to an area. A feeder supplies 2 megawatt to an area. Full stop. The total losses at peak load are 100 kilowatt. The total losses at peak load are 100 kilowatt. The total losses at peak load are 100 kilowatt. And units supplied to that area and units supplied to that area and units supplied to that area during an year and units supplied to that area during an year are ARER are 5.61 million. 5.61 million. Full stop. Calculate the loss factor and average power loss. Calculate the loss factor and average power loss. Once again, and read the question. A feeder supplies 2 megawatt to an area. Full stop. The total losses at peak load are 100 kilowatt. The units supplied to that area during an year are 5.61 million. Full stop. Calculate the loss factor and average power loss. You can observe that problem. They given peak load, right? Maximum demand or peak load 2 megawatt. Write down given data. Maximum demand or peak load equal to 2 megawatt. Maximum demand or peak load equal to 2 megawatt. So to losses at peak load, that is nothing but power loss at peak load. Losses at peak load is nothing but power loss at peak load equal to 100 kilowatt. Power loss at peak load equal to 100 kilowatt. Number of units supplied per year. Number of units supplied per year. PER per. Number of units supplied per year equal to 5.61 million. 5.61 million. That is equal to 5.61 into 10 power 6 kilowatt hour. Units supplied per year equal to 5.61 million. That is equal to 5.61 into 10 power 6 kilowatt hour. Right. So they are asking determine the loss factor, power loss. So to find out the loss factor is nothing but generally loss factor is equal to average power loss to the power loss at peak load. We don't know average power loss. We just know the power loss at peak load, but we don't know average power loss. That's why we don't use loss factor direct formula. So at that time we can utilize approximate formula. So FLS is equal to FLD 0.3 FLD plus 0.7 FLD square, right? But FLD we don't know. So for that FLD you have to determine first of all. Write down FLD equal to, I mean load factor equal to number of units supplied per year divided by maximum demand into 8760. FLD equal to number of units supplied per year divided by maximum demand multiplied by 8760. Therefore 5.61 into 10 power 6 divided by 2000 into 8760. 5.61 into 10 power 6 divided by 2000 into 8760. So value is load factor value FLD equal to 0.32. The value of load factor equal to 0.32. Now determine loss factor by using approximation formula. So loss factor FLS is equal to loss factor FLS is equal to 0.3 FLD plus 0.7 FLD square. Loss factor FLS is equal to 0.3 FLD plus 0.7 FLD square. Therefore, that is equal to 0.3 into 0.2, sorry, 0.32. 0.3 into 0.32 plus 0.7 into 0.32 square. 0.3 into 0.32 plus 0.7 into 0.32 square. That is equal to FLS is equal to 0.168. Loss factor is equal to 0.168. So, therefore, next, determine the load factor and loss factor. Now, direct formula for loss factor. Loss factor is equal to average power loss divided by power loss at peak load. Loss factor equal to average power loss divided by power loss at peak load. So you have to determine average power loss, right? So average power loss is equal to loss factor multiplied by power loss at peak load. Average power loss is equal to loss factor multiplied by power loss at peak load. So therefore, average power loss equal to 0.168 multiplied by what is power loss at peak load? 100 kilowatt. So 0.168 multiplied by 100. Therefore, average power loss is equal to 16.8 kilowatt. So average power loss is equal to 16.8 kilowatt. Right. So look, just you can observe FLD is 0.32, but FLS 0.168. So that's why. So that formula, that derivation, after completion of all three cases, we can conclude the one sentence: FLD square less than FLS less than FLD, right? That will be suitable for this problem. Last one line, write down. The loss factor should be as low as possible. The loss factor should be as low as possible. Loss factor should be as low as possible, so that energy efficiency will be very high. So that the energy efficiency will be very high. Energy efficiency will be very high. In general, FLD square less than FLS less than FLD. FLD square less than FLS less than FLD. Right. All of you write down or not? Okay. If you write down, now
Sir,
note down the number 4.
sir, last point ఒకసారి చెప్పారు సార్.
Okay.
The loss factor.
Loss factor should be as low as possible. The loss factor should be as low as possible, so that the energy efficiency will be very high.
Okay, sir.
In general, FLD square less than FLS less than FLD. మీరు ఇంకా మాకు బాగా గుర్తుంది, మాకు టైం ఉంది అనుకుంటే, సపోజ్ యూ హ్యావ్ టు టైమ్ ఇన్ దట్ ఎగ్జామినేషన్, just you have to draw the characterization of relation between load and loss factor. Already you have to draw in the relation derivation. That graph is also drawn in this problem also. No need to draw the graph, but for our satisfaction. Okay, good. Now note down the problem number 4. So this is the important problem, and most of the times problem number 4 also asking in the examination. right? So problem is a primary feeder is supplying annual peak load input of 2000 kilowatt, comma, the total copper losses at the time of peak load is 100 kilowatt. The total annual energy supplied to the sending end of the feeder is 5.61 into 10 power 6 kilowatt hour. Calculate the annual loss factor and also calculate the total annual copper loss and its value at $0.03 per kilowatt hour. Normal problem already you have to done the before problem like that we have to solve this problem also, but second case calculate the annual loss factor, there is no problem, you have to already solve the problem. Coming to the calculate total annual copper loss, that is nothing but annual power loss. To find out loss factor first, after then find out power loss, then to multiply the $0.03. Every unit they require $0.03. Suppose they are asking in rupees, you can convert this into 60 rupees, 70 rupees or 60 rupees also, but they don't ask in conversion, just in dollar, answer also in dollar, right? As usual. So a primary feeder is supplying annual peak load of input 2000 kilowatt, that is demand. So and copper loss at time of peak load. So this is the maximum demand 2000 kilowatt and losses at peak load, that is nothing but power loss at peak load is 100 kilowatt, same as before problem. So maximum demand 2000 kilowatt, power loss at peak load 100 kilowatt and annual energy supplied to the sending end, that is nothing but number of units supplied, total annual energy supplied equal to 5.61 into 10 power 6 kilowatt hour, right? So calculate the loss factor, same ditto problem as we have to done in the before problem. So we know the load factor, that is equal to average load by peak load. Average load is nothing but number of units supplied divided by peak load into 8760 hours. Why? Because annual. So number of units supplied is nothing but 5.61 into 10 power 6 kilowatt hour divided by peak demand or peak load or maximum demand, whatever it may be. That is the 2000 kilowatt multiplied by 8760. Right? So the value is 0.32. Same ditto. Before problem also load factor is 0.32 na. Now loss factor is also 0.168. I think. Load factor is average load by peak load. Average load is nothing but number of units generated by hours in a year. So number of units generated by hours in a year is nothing but 8760 divided peak load. So 5.61 10 power 6 divided by 2000 into 876, that is 0.32, right? Now loss factor. By using approximation formula, loss factor is equal to 0.3 FLD plus 0.7 FLD square. So 0.3 into 0.32 plus 0.7 into 0.32 square. Value is already before problem, same as before problem, 0.1676, otherwise 0.168. 0.1676, otherwise 0.168. Now loss factor, from the loss factor formula, loss factor is equal to average power loss to the peak load power loss. Therefore average power loss is equal to loss factor multiplied by the peak load power loss. So loss factor is equal to 0.168 multiplied by peak load power loss 100 kilowatt. So average power loss is equal to 16.8 kilowatt, same as before problem, but only one change. So now this value must be multiplied with $0.03 value. So total annual copper loss equal to, so annual means into 8760 hours first of all. Total annual copper loss. So this is the average power loss, right? First you have to find out average power loss. Now annual means into 8760. 16.81 multiplied by 8760 is nothing but annual copper loss. The value is 1,47,000 kilowatt hour. Now for kilowatt hour $0.03. Now 1,47,000 kilowatt hour is nothing but multiplied by 0.03. So cost of total annual copper loss is equal to 1,47,000 kilowatt hour multiplied by $0.03. So kilowatt hour cancel, only dollar value will be available. Suppose they are asking, suppose they given rupees, 5 rupees, 6 rupees. Now multiplied 1,47,000 into 6 rupees. Like that. So the value is right. Please note down. Next problem number 5. A 120 megawatt substation delivers 120 megawatt for 3 hours, 60 megawatt for 8 hours and shut down for rest of each day. So this problem also somewhat important. I think only one time asking in JN2 papers. Say 120 megawatt substation delivers 120 megawatt for 3 hours, 60 megawatt for 8 hours and shut down for the rest of each day. That means, so 3 hours is 120 megawatt, 8 hours is 60 megawatt, 3 plus 8 is nothing but 11 hours. So 11 hours only operating that substation. Remaining 13 hours will be rest. That is the meaning of that one. So full stop. It also shut down for maintenance for 15 days each year. For 1 day of the hours will be rest. For 15 years, sorry, 1 year, 15 days for shutdown for maintenance. Right? Calculate its annual load factor. Right? So don't write down solution. First I am giving some clarification. Given data, write down 120 megawatt substation delivers 120 megawatt substation delivers, right? Under that one, please take a table, only 2 columns. Load megawatt, 1 column, another column time hours. 120 megawatt substation delivers. Under that one, take table with 2 columns. First column load megawatt, another column time hours. So in load column 120 megawatt, write 120. In time column write 3. In load column 60. In time column 8. So table close, right? Remaining will be shut down. We don't bother about. Just So take in table 2 columns, load megawatt, time hours. 120 in load table 120 60, in time 38. Now we can easily observe that what is the maximum demand. What is the maximum demand is nothing but 120 megawatt, right? So write down. So below that table, write down maximum demand or peak load equal to 120 megawatt. Maximum demand for our peak.
సార్ స్క్రీన్ మీద ప్రాబ్లం కనిపించట్లేదు సార్.
అవునా?
ఇప్పుడు
స్క్రీన్ కనిపించలేదా?
ఇప్పుడు కనిపిస్తుంది, ఇందాక నుంచి కనపడలేదు.
ఓకే, అంటే నేను చాలా సేపు నేను మౌస్ నేను క్రసర్ని ఆన్ తిప్పలేదు కదమ్మా, దానివల్ల.
ఓకే సార్.
సో maximum demand or peak load equal to 120 megawatt, right? Now energy supplied for each working day equal to, energy supplied for each working day equal to, don't write this value first, we can write some theory, after then write these values. Energy supplied for each working day equal to energy delivered for 3 hours plus energy delivered for 8 hours. Energy supplied for each working day equal to energy delivered for 3 hours plus energy delivered for 8 hours. That is equal to 120 into 3. 120 megawatt operating 3 hours, 60 megawatt operating 8 hours. That's why 120 into 3 plus 60 into 8. That is equal to 840 megawatt hour. 840 megawatt hour. 840 megawatt hour, right? Generally they don't given maintenance for 15 days means, so we can utilize that 840 directly. 840 by maximum demand 120 into 8760, but they given the total substations shut down for 15 days every year. That's why you have to reduction that 15 days. So right number of days substation works on each year. Number of days substation works on each year. Number of days substation works on each year. That is equal to number of days in a year. Number of days in a year. Number of days in a year minus number of days shut down for maintenance. Number of days in a year minus number of days shut down for maintenance. So that is equal to 365 minus 15. So number of days in a year 365 and 15 days will be shut down every year. That's why 365 minus 15, that is equal to 350 days. So therefore energy supplied per annum, energy supplied or number of units generated, whatever it may be, number of units generated, number of units supplied, energy delivered, whatever, all are units. Units in the sense megawatt hour or kilowatt hour. So energy supplied per annum equal to, energy supplied per annum equal to 840 into 350 days only. Working is 350. Each day 840 megawatt. So that's why 840 into 350, that is equal to 294 into 294 into 10 power 6. 294 into 10 power 6 kilowatt hour. Kilowatt hour. 294 into 10 power 6 kilowatt hour. Why I am taking kilowatt hour means, so actually to multiply 840 into 350, 294,000, 3 zeros. Megawatt is nothing but 10 power 6. So that 3 zeros goes to the kilo and mega is nothing but 10 power 6. Why I am taking 10 power kilowatt hour is nothing but next we have to determine the load factor, right? So that's why I am taking kilowatt hour. Now annual load factor equal to FLD equal to annual load factor equal to annual load factor equal to energy supplied per annum. Annual load factor equal to energy supplied per annum divided by peak load into annual operating hours లేదా annual working hours. Annual load factor equal to energy supplied per annum divided by peak load multiplied by generally number of hours in a year, బట్ ఇక్కడ ఇయర్ మొత్తం పనిచేయలేదు కాబట్టి సో యాన్యువల్ ఆపరేటింగ్ అవర్స్ అదర్వైజ్ యాన్యువల్ వర్కింగ్ అవర్స్ యాజ్ యువర్ విష్. Annual load factor equal to energy supplied per annum divided by peak load into annual working hours. So that is equal to 294 into 10 power 6 kilowatt hour divided by maximum demand is nothing but peak load or maximum demand 120 megawatt into 350 into 350 days. The substation will working 350 days for a day 24 hours. That's why 350 into 24. 294 into 10 power 6 divided by 120 into 350 into 24. The value of load factor is 0.29. Value of load factor is 0.291. 0.291. Therefore, annual loss factor, approximate formula. Therefore, annual loss factor equal to annual loss factor equal to 0.3 FLD plus 0.7 FLD square. So that is equal to 0.3 into 0.29 plus 0.7 into 0.29 square. So therefore annual loss factor equal to 0.14. Value of annual loss factor equal to 0.14, right? So okay, next simple problem, sixth problem. A 50 megawatt hydro generator delivers 320 million kilowatt hour. A 50 megawatt hydro generator delivers 320 million kilowatt hour during the year. So calculate the plant load factor. Right? General already simple problem. So load factor is nothing but average load by maximum demand, right? But we do average, what is meant by average load is nothing but number of units delivered or supplied, number of units generated divided by hours in a year. So annual average load is equal to number of units generated divided by hours in a year. That is equal to number of units generated divided by 8760. So they given during the year that delivers 320 million kilowatt hour. Million is nothing but 10 power 6 as usual, not 106, So this is not 106, this is 10 power 6. 320 into 10 power 6 divided by 8760. 320 into 10 power 6 divided by 8760. So that is equal to 36.529 megawatt. 36.529 megawatt. Now find out load factor. Plant load factor equal to average load by peak load. Plant load factor equal to average load by peak load. 36.529 megawatt. 36.529 megawatt divided by 50 megawatt. Because a 50 megawatt annadu. So that's why 36.529 megawatt by 50, that is equal to 0.772. 0.72, that is the load factor value. So next problem, a substation is to supply an urban area having the following particulars. A substation is to supply an urban area following particulars. First one, 1000 houses with an average connected load of 2 kilowatt in each house. In every house, 2 kilowatt is the connected load. So for that 1000 houses, the demand factor is 0.4 and diversity factor is 2.5. Right? 1000 houses with an average connected load of 2 kilowatt. For that 1000 houses, demand factor is 0.4 and diversity factor is 2.5. Second one, 15 factories having an overall maximum demand of 100 kilowatt. 15 factories having an overall maximum demand of 100 kilowatt. Right? Third one, 10 bore wells of 7 kilowatt each and operating together in the morning. 10 bore wells of 7 kilowatt each and operating together in the morning. Full stop. The diversity factor among above three types of customers is 1.2. So total diversity factor, that is nothing but 1.2. What should be the minimum capacity of the substation? What should be the minimum capacity of the substation? Right? To find out the capacity, that is nothing but to find out the rating of the substation. So first of all, they given individual demands. 1000 houses will be there, bore wells is there, and 15 factories is there, right? So for that, we have to find out the sum of individual maximum demands. Why? Because they given diversity factor, right? All of you write down the problem or not? Write down the problem. Why? Because I am going to next page, that's why. Write down or not?
Sir, 1 minute, sir. 2 lines next.
Okay. That's why I'm asking. Please write down. So here they given individual demands or individual loads. So that's why first of all you have to find out the sum of individual maximum demands of the houses. So 2 into 2 kilowatts into demand factor 0.4 into 1000. Total houses 1000. Every house 2 kilowatt with a demand of factor of 0.4. So this is the formula. Why? Because demand factor is equal to maximum demand by connected load. Therefore, maximum demand is equal to demand factor into connected load. To find out maximum demand, that is equal to demand product of demand factor into connected load. Here, this is the connected load and demand factor is 0.4. 2 into 0.4 into 1000, that is 800 kilowatt. Therefore, maximum demand similarly, the maximum demand factor is 100 kilowatt. Agriculture maximum demand, that is borewell maximum demand. So 7 bore wells, each one 10 kilowatt. So maximum demand 10 into 7, 70 kilowatts. So they given 4 individual loads. That's why we have to first of all to find out individual maximum demands for 1000 houses, factories, then bore wells. Now, to determine sum of maximum demands of 3 types of loads. So 320 plus 100 plus 70, that is 490 kilowatts. And they given diversity factor of combined 3 types, that is 1.2. And they given maximum demand of the station. So this is the maximum demand of the station, 490 kilowatt divided by diversity factor. What is the formula? Diversity factor equal to sum of maximum demands divided by maximum demand of the station. So to find out maximum demand of the station, sum of maximum demands divided by diversity factor. So maximum demand of the station is equal to sum of individual loads, otherwise sum of maximum demands divided by diversity factor, 490 kilowatt by 1.2. So the value is 408.33 kilowatt. Right? So this is the minimum capacity of the substation is 408.33 kilowatt. Individually, agriculture is 70 kilowatt, factory is 100 kilowatt, and houses 320 kilowatts. So total capacity of the substation is nothing but maximum demand of the station is equal to the capacity of the substation. So that's why, so maximum demand on the station equal to 408.33 kilowatt, that is equal to capacity of the substation, 408.33 kilowatt. So please note down from this problem, next problem onwards, from 8th problem onwards, I will explain next class.